All right, welcome to week 14. I do realize that we have a quiz and a project this week, but I do want to go over some last loose ends with this unit about 2D shapes before we roll into our new unit next week, which will be about 3D shapes. We've talked about a lot of stuff, but there's just a random few ones about shapes that are bigger. Shapes that have more sides than quadrilaterals, and that's what we're going to be looking at today. So first thing we need to do is have a word for those shapes. And the word we're going to use the most is polygon. And we've used this word before, but we have not defined it on our Freyer model papers, even though we have defined it in class. So if we remember that definition, it is I'm not too sure why all of these are crazy sizes. The definition of a polygon is a closed, straight-sided shape. All right. And then one fact about it is we use the variable n to represent the number of sides. And in this case, that also means the number of angles. So some examples that we're familiar with, right? We could have a right triangle, we could have a rectangle, parallelogram, all of our different types of quadrilaterals, right? Trapezoid. We could have something that looks like a house, that's technically a pentagon, right? Or something that, right, kind of goes crazy like a crown, but that would be 1, 2, 3, 4, 5, 6, 7 straight sides, right? To that polygon. We could have something that is even more crazy, right? And you might want to use some of these shapes in your project, which we would have to decompose these into shapes we could find the area of for our project. Some examples that are not polygons would be anything with a curve, like a semicircle or a Pac-Man shape, or something that's not closed, which means not all the sides are connected. All right. So we're going to learn something about polygons and then also learn one special case of polygons. So the first thing that we're going to talk about are the angles inside of a polygon. And we know some of those angles already. If we have a triangle, doesn't matter what type of triangle it is, we know something about all three of these triangles. It's that all three of their angles, right, no matter what type of triangle it is, those angles will always add up to 180. We've used that before. We've studied it. We made formulas for it. We then built off of that to find exterior angles. We did a lot of work with that fact. But what we haven't done is try to say, well, what if we have a rectangle or a trapezoid or a parallelogram? We've talked about some of their individual angles, right? Like in a rectangle, we have 4 90-degree angles, or in a trapezoid, these two angles are supplementary, and these two angles are supplementary, or in a parallelogram, opposite angles are congruent, but angles on the same side are supplementary. But we haven't talked about what they add up to. And it's not actually too difficult, right? We can use the fact that in a triangle, the three angles add up to 180 to help us with a more complex shape. So in a rectangle, we can split it into two halves, right? And both of those triangles are both 180. So we can add that together to get 360, right? 2 times 180 is equal to 360. We also could have done 4 times 90 because in a rectangle, we know what the size of those angles are. But with a trapezoid, we don't, right? So again, we can cut it into two halves and get, again, two separate triangles but both have 180. So this shape has 4 sides, and again, we get 2 triangles, right, that both have 180 in it. So again, we get 360. Some of you might be thinking, how can we not split it up into more than 2 triangles, right? We did it like this, we would get 4 triangles. But there's an issue with this, because notice how if we start looking at individual angles, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 12 angles here. 4 of them are not in the corners of our original shape. So those 4 corners will be not accounted for, and it'll cause issues for us. So when we break up shapes into triangles to figure out the sum of their angles, we always have to make sure that we use only the corners of the shape. So we can do this, right? Or the only other way to do would be to use the other diagonal in a quadrilateral. All right. In either case, the only way we can split up a quadrilateral is into 2 triangles, so we will always get 360. All right. But let's look at some more complicated shapes. What if we had a pentagon? Doesn't matter how the pentagon looks, right? This one's a little lopsided. That's fine. But we want to talk about how can we split this into triangles where the corners of the triangle are also in the corners of the pentagon. I have a favorite way of doing this, and that's to choose one corner and just connect it to all the other corners. And those are my triangles, right? I have 1 triangle, 2 triangles, right? 1, 2, 3. All right, 3 triangles. So I have 3 triangles times 180, because that's 180 degrees in each. So here I get 540. What if I had a hexagon? All right, again, my method, pick one corner, connect that corner to all the other ones, and then count up how many triangles I have. I have 1, 2, 3, 4. So with a hexagon, I get 4 triangles times 180, which would be 720 degrees. What if I have a 7-sided shape? Can't remember off the top of my head the name of that. All right. So I can pick one corner, connect it to all the other corners, and then count up how many triangles I have. So in that 7-sided shape, I got 5 triangles, so I got 5 times 180, and that would give me 900. And let's just do this one more time, because I can actually draw an octagon pretty well, right? Because it's just a stop sign. And then I pick one corner, connect it to all the other corners. 1, 2, 3, 4, 5, 6. Right? I don't want to have to do this every single time. And there is a quick way to do this if we know how many sides the shape has to figure out what all of the angles add up to. All right? We might have noticed that pattern already. So let's look at it. In a triangle, we have 3 sides, which made one triangle, which means we got 180 degrees for the sum of interior angles. So if we continue, if we had a quadrilateral, we had 4 sides, we split that up into 2 triangles, so we got 360. For a pentagon, we have 5 sides, got 3 triangles, so then that means we got 540. In a hexagon, we got 6 sides, which means we got 4 triangles, which means then we got 720. And we kept going, right? 7 was 5 triangles, which is 900. 8 sides, we got 6 triangles, and then that means we got 1080. we might see the pattern here. If we have n number of sides, that means we do n minus 2. That's the number of triangles that we have. And then our math was just n minus 2 times 180. So that's our formula. Let me write that here. The sum of interior angles is equal to n minus 2 in parentheses times 180. And then we can add that to our Freyer model as well, which I'll post online. The sum of interior angles is equal to n minus 2 times 180 degrees. Nice, simple formula, just subtraction, multiplication, nothing more complicated than that. But what we're going to do next is just to say, but what if our shape is symmetrical? What if all of the angles are the same? What if all the sides are the same? That makes a shape pretty special, right? We have equilateral triangles, right, where all 3 sides are the same. We have squares, where all 4 sides are the same and all 4 angles are the same. And then we start having what we call regular polygons. And for a pentagon, it looks just like the building, where it has, the definition would be a polygon that is equilateral, which means all of the sides are the same, and equiangular, which means all of the angles are the same. So let's add that to our Freyer model. We have regular polygon, a polygon whose sides and angles are all the same, right? And our examples are just those normal shapes that we're all used to, that we see when we talk about what the name of the shape is, nothing messy or anything like that. Some non-examples would be a rectangle, right? Because all the sides aren't the same. It could be a pentagon. 1, 2, 3, 4, 5, right? A pentagon. It has 5 sides, but none of them are the same length and none of the angles are the same. We have the same fact as the other one, where the sum of interior angles is equal to n minus 2 times 180, but because all of the angles are the same, we can even go one step further. Is that to say, in a pentagon, we know all of those angles add up to, what have we been saying? 540. And then we divide by 5 to say that each one has to be 108. In a square, we said 360 divided by 4 would be 90. In a triangle, we did 180 divided by 3 to get 60. So the size in a regular polygon, the size of an interior angle is equal to the sum divided by n. So if we plug in that, we get n minus 2 times 180 over n. All right, so let's add that to our Freyer model, and then we'll do one quick example. So our second formula that we can use is that each individual interior angle, because they're all the same, would be the sum divided by how many angles there are. So let's look at an example. Let's say we have a 20-sided regular polygon. I definitely don't want to draw that, and I'm definitely not going to get it to be regular, because no matter how careful I am, there's no way that I can do that by hand in a quick and easy way. But we can figure out, using our formulas, how much all of the angles add up to and how much each individual angle has to be if it is regular. So just to get a sense of what this could look like, right? 1, 2, 3, 4, 5, 6, 7. Too many sides, right? And I don't know how to do that, but we can get a sense for what the shape looks like. It's starting to look pretty circular, but with straight sides. But we can figure it out, right? The sum of all 20 of those angles is going to be equal to 20 minus 2 times 180. So we get 18 times 180. And that's something I'm going to definitely have to use my calculator for. So that's 18 times 180 is 3,240. If we wanted to be lazy, we can use the Greek letter epsilon. To represent the sum. That's something that we use in math all the time. But then each individual angle, right? Each individual angle on the inside is going to be equal to the 3,240 divided by, and there's 20 of them, so divide by 20. So each angle is going to be 162 degrees. So that means this angle is 162, this angle is 162, and we can figure that out no matter how many sides it has using our formulas. All right? So that was the video that you need to watch for this week, just to wrap up some of these loose ends. There will be a second video that is optional that will cover the area of regular polygons. We could always decompose it into other things. This is only necessary if you did draw, for some reason, a regular pentagon or a regular octagon in your project and you want to use this formula. It's not an easy formula to use, but it is a formula that works.